Hello everyone, I'm Chen Wen. In this talk, I'm going to introduce our paper, Controlled Concurrency Testing via Periodical Scheduling. This is a joint work of Shenzhen University, Decider University, and Huawei Technology Company Limited. First, I will briefly introduce the background of controlled concurrency testing. Concurrent programming is now prevalent, but correctly designing and implementing concurrent programs is difficult, and it is easy to introduce concurrency bugs, becoming a serious threat or leading to economic losses. Testing concurrent programs for defect is hard due to the non-determinism of multi-thread execution. Since concurrency bugs often can only be exposed through specific thread interleaving, traditional testing techniques without any scheduling control often cover only a portion of schedule space, failing to explore the order in which the bug may reside, even if the program is tested over and over again. Controlled concurrency testing technique offer a promising solution for concurrency bug detection. Their key insight is to control the order in which threads get executed and explore the space of possible interleaving to detect bugs. Such techniques require taking over the scheduling in a program. By controlling scheduling decisions in either a systematic or non-systematic way, they can reliably explore the schedule space of thread interleaving. However, various challenges remain in current controlled concurrency testing technique, rendering them ineffective and ad hoc. A key practical challenge for controlled concurrency testing is how to achieve controlled scheduling. We expect to test lots of different thread interleaving in a limited time. Thus, the scheduling approach should be efficient. Real-world programs use a plethora of synchronization primitives. We also need a scheduling approach that doesn't have pathological interaction with the synchronization option in the target program. Another key challenge is how to effectively explore the schedule space. Exhaustively enumerating all possible thread interleaving is often practically infeasible. The number of thread interleaving grows exponentially with the number of threads and the length of program execution. Randomized techniques often provide probability guarantee of finding bugs. Systematic techniques tend to go through a larger schedule space than needed, requiring more overhead or missing some bugs. Therefore, we still need an effective way to explore the schedule space. Next, I will illustrate a simple motivating example and give a high-level overview of our proposal. The figure shows an example simplified from a CVE. Two threads concurrently invoke the function once and are synchronized with the help of three variables: log, waiters, and down. The variable log allocated in the main function and released in the child thread is used to protect the critical section. The variable waiters indicate the number of threads waiting to enter the critical section. The variable down will be set to 1 once the critical section is complete, and other thread created later may return directly. The expected behavior is that only the last thread should release the log. Traditional testing does not explicitly control the thread schedule. Therefore, such testing often ends up executing the same thread interleaving many times and difficult to find concurrency bugs. The synchronization of this program are well designed. However, there are still three kinds of concurrency bugs in this program. there are non-pointer dereference, use after free, and double free. All these bugs are actually hard to trigger, as they require a specific order of operation on variable down, waiters, and log. When applying controlled concurrency testing to this example, one will control the thread scheduling and test the program by systematically or randomly iterating the scheduling decision on each instruction. Such an naive approach goes through a large schedule space and difficult to find bugs. We need to find out an efficient and effective solution for these two challenges: how to achieve controlled scheduling and how to effectively explore the schedule space. To tackle the aforementioned challenges, we propose a novel systematic controlled concurrency testing technique called Period. It uses periodical execution, an efficient and non-preemption way to achieve controlled scheduling. It also employs many key techniques to heavily reduce the schedule space, such as schedule bounding, dynamic keypoint slice, schedule prefix, and the para-scheduler. Considering the motivating example, to achieve controlled scheduling, Period uses a series of execution periods to host the execution of the target program. The execution of a concurrent program is modeled as periodical execution, and each period only executes part of the instruction. The context switches can be achieved via period switches naturally. The schedule exploration starts with the smallest possible period number, that is 2, which only allows one context switches. Once all schedules within the period number are explored, it increases the period number by 1 to carry on exploring until either all possible schedules are explored or the period number reaches the preset bound. Note that we didn't iterate the scheduling decision on all the instructions of the program. Instead, we explore the schedule space gradually, targeting feasible interleaving. We first assume that each thread only contains one key statement and execute 2 different thread interleaving. After analyzing the runtime information, we obtain a pair of symmetry dynamic slices. We carry on exploring based on the newly obtained dynamic slice. After exploring fine schedule, a new dynamic slice is found and needs to be explored. Moreover, a schedule prefix that contains necessary context switches to reach this dynamic slice is used to guide the schedule exploration. Again, Period will systematically explore each newly obtained dynamic slice. Finally, Period stops the exploration when all the obtained dynamic slices are explored within the preset period number bound. In this example, the period number bound is set to be 6 or any larger number, so that the non-pointer dereference, use after free, and double free bug can be found. We shall now present some essential technical details. Let us take a quick look at the workflow of Period, which contains 3 main components: schedule generator, periodical executor, and feedback analyzer. Given the source code of the target program and a valid test input, the schedule generator systematically generates schedule and feeds them to the periodical executor. The periodical executor actively controls the thread interleaving of the target program, following the schedule generated by schedule generator. The feedback analyzer makes use of runtime information to guide the schedule generator to effectively generate legal schedule to cover more untested interleavings. Specifically, Period first applies static analysis on the source code to identify key points. Key points are statements or instructions that are key to the program observable behavior, such as statements accessing shared memory or synchronization primitives. Capturing the key points instead of all the statements enable filtering out redundant interleaving. The schedule generator generates schedule according to the number of key points, and then feeds them to the periodical executor. A schedule is a series of execution phases that contains thread identifiers. The schedule generator employs a schedule bounding technique to systematically generate schedule. The key idea of schedule bounding is to bound the number of context switches that are allowed in a schedule, as many railroad concurrency bugs have a very small bug depth. As shown in this simple example, Period explores schedule systematically with an increasing number of period number bound. It can quickly find a non-pointer derivative bug on the fifth schedule. The periodical executor enforces the generated schedule in the execution. The periodical executor uses a series of periods to host the execution. Key points assigned to a period only get to be executed when the previous period is completed, and each period has a lifetime, which should be long enough to cover the key points hosted in any period. In this way, context switches can be achieved via period switches. The feedback analyzer makes use of runtime information, such as key point, dynamic key point slice, and schedule prefix to guide the schedule generator to effectively generate legal schedule. Here, we briefly introduce the dynamic key point slice. It contains the key points of each thread that are covered by a dynamic run, and it records the country paths executed by each thread. Period aims to find all dynamic key point slices and test each of them with all possible schedule. Exploring schedule based on dynamic key point line instead of all the key points can help avoid exploring redundant schedule. A schedule prefix is a partial schedule that contains context switches need to reach a dynamic key point slice. The schedule prefix is used to leave the execution of the target program to the dynamic key point slice as possible. Generating schedule satisfying the prefix help avoid exploring infeasible schedule. In addition, Period can equip the parascheduler. The parascheduler allows the isolation of a specific order on field statement while letting the rest of the program execute concurrently. This optimization makes it possible to hugely reduce the schedule space to explore when there are many working threads. Let's go back to our motivating example. First, all the statements that access shared memory location or contain synchronization primitives are identified as key points. At the beginning of the schedule exploration, we assume that only the first key point can be covered. The schedule generator generates two schedules that only allows one context switch, and the periodical executor executes two different thread interleaving. After analyzing the runtime information by the feedback analyzer, we obtain a pair of symmetry dynamic key point slices. We carry on schedule exploration based on the newly obtained dynamic key point slice. The schedule generator continues to generate schedule with 3 periods that allow 2 context switches. When testing the 5th schedule, a new dynamic key points line is found and need to be explored. Moreover, a schedule prefix that contains necessary context switches to reach these dynamic key points lines will be used to guide the further schedule exploration. Again, period would systematically explore each newly obtained dynamic key points line. Finally, period stop the exploration when all the obtained dynamic key points lines are explored within the preset period number bound. In this example, the period number bound is set to be 6 or any larger number, so that the non-pointer dereference used after free and double free bug can be found. We had implemented and performed a thorough evaluation of period on a variety of benchmarks. This is the experimental result on CVE benchmark, including 10 real-world CVE. For comparison, we have selected 6 well-known and representative control concurrency testing techniques, 2 recent work that use predictive analysis, and also 3 data race detectors. The results show that period successfully identify more bugs than other competitors. Here is the first half of the table, showing the experimental result on SCT bench. The result includes the version of period equipped with our serialized scheduler. We call it serial. We can see that our parallelized scheduler improves serialized 1 in terms of schedule space, enabling us to detect more bugs. And here is the second half. The results show that both period and serial outperform other controlled concurrency testing techniques in terms of concurrency bug finding ability. We also evaluate the runtime overhead required for achieving controlled scheduling. We can see that period incurs some noticeable runtime overhead, which is much lower than other competitors. In summary, we present a controlled concurrency testing technique called period. It achieves controlled scheduling through periodical execution, and it performs systematic testing on each dynamic key points lines of the concurrent program with schedule bounding technique. It also uses schedule prefix to guide the schedule generation and allow paraschedule to hugely reduce the schedule space. It outperforms state-of-the-art control concurrency testing technique on a variety of benchmarks. You can try our artifact out from this link, and at this point, we will be happy to take any question. Thank you.